Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Computer and Information Sciences, SOCIS, Postgraduate Diploma in Computer Applications, PGDCA, New. Semester 2, MCS 207 Database Management Systems. Block-1 The Basic Concepts. Unit-3 Entity Relationship Model, 3.0 Introduction. In the previous unit of this block, you have gone through the concept of relational database management systems and one of the important languages for relational database relational algebra. This unit explains you about of an analysis model of the database system, known as Entity Relationship (ER) model. The ER model is a widely used model for analysis of data requirements of an organization. The AR model is primarily a semantic model and is very useful in creating raw database design that can be further normalized. With the availability of object-oriented technologies, the ER model has been extended to include object-oriented features. This unit also discusses these ER extensions. We will also discuss the conversion of ER diagrams to tables in this unit. 3.1 Objectives. After going through this unit, you should be able to define and explain various components of ER model. Draw an ER diagram for a given problem. Convert an ER diagram to a relational database. Explain the role of extended features of ER model. Convert an ER diagram to relations. 3.2 Entity Relationship ER model. Some of the important characteristics of ER model are listed below. Entity Relationship Model is a high-level conceptual data model. It allows you to describe the data involved in a real-world enterprise in terms of entities and their relationships. It is widely used to create an initial design of a database. It provides a set of useful concepts that make it convenient for a developer to move from a basic set of information to a detailed and precise description of information that can be easily implemented in a database system. It describes data as a collection of entities, relationships and attributes. In the following sections, we explain the basic terms used in the ER model. 3.2.1 Entities. First, let us answer the question, what are entities? An entity is an object of concern, which is used to represent the things in the real world, e.g., car, table, book, etc. An entity need not be a physical entity, it can also represent a concept in the real world, e.g., project, loan, etc. It represents a class of things, not any one instance, e.g., student, entity has instances of Ramesh and Mohan. Entity set or entity type, a collection of a similar kind of entity is called an entity set or entity type. For the college database, the objects of concern are student, faculty, course, and department. The collections of all the students' entities form an entity set. Student. Similarly, collection of all the courses form an entity set course. You may please note that entity sets need not be disjoint. For example, an entity, say Mohan, may be part of the entity set student, the entity set faculty and the entity set person. Entity identifier, key attributes. An entity set usually has one or more attributes, which attains unique value for every distinct entity in a given entity set. Such an attribute or set of attributes are called key attributes, and its values can be used to identify each entity uniquely in the given entity set. Strong entity set. An entity set which contains at least one key attribute is a strong entity set. For example, a student entity set would contain at least one key attribute, enrollment number, which is unique for every student. Thus, the entity set student is a strong entity set. Weak entity set. Entity sets that do not contain any key attribute, and hence cannot be identified independently, are called weak entity sets. A weak entity cannot be identified uniquely by its attributes, therefore, are recognized in conjunction with the primary key attributes of another strong entity on which its existence is dependent, called owner entity set. Generally, a primary key of an owner entity set is attached to a weak entity set, which has identifying attributes, called discriminator attributes. These two together form the primary key of the weak entity set. The following restrictions must hold for the above The owner entity set and the weak entity set must participate in one-to-many relationship set. This relationship set is called the identifying relationship set of the weak entity set. The weak entity set must have total participation in the identifying relationship. One of the most common examples about the weak entity set is an entity set dependent and the related strong entity set employ in an organization. The dependent entity set is used to list all the dependents of each employee of an organization. The attributes of the dependent entity set are dependent name, birth date, gender and relationship with the employee. Each employee entity is said to own the dependent entities that are related to it. However, please note that the dependent entity does not exist of its own, it is dependent on the employee entity. In other words, you can say that in case an employee leaves the organization, all dependents related to him, her also leave along with this employee. Thus, a dependent entity has no significance without the entity, employee. Thus, it is a weak entity. 3.2.2 Attributes. Let us first define what is an attribute. An attribute is an element of an entity which can contain a representative value. In other words, an entity is represented by a set of attributes. For example, a student entity set may consist of attributes: roll no, student's name, age, address, course, etc. An entity will have a value for each of its attributes. For example, for a particular student, the following values can be assigned. Roll no, 1234. Name, Mohan. Age, 18. Address, Z894, Maidan Gari, Delhi. Course, B, SC. H. Domains. Each simple attribute of an entity type contains a possible set of values that can be attached to it. This is called the domain of an attribute. An attribute cannot contain a value outside this domain. Example for student entity age has a specific domain. Integer values say from 15 to 90. Types of attributes. Attributes attached to an entity can be of various types. They are explained below. Simple, an attribute that cannot be further divided into smaller parts and represents. The basic meaning is called a simple attribute. For example, each of the attributes first name, last name, age of person entity set are simple attributes. Composite, attributes that can be further divided into smaller units and each smaller unit contains specific meaning. For example, the attribute name of a faculty entity can be subdivided into first name, last name and middle name. Single valued, attributes having a single value for a particular entity. For example, age is a single valued attribute of a student entity. Multi-valued, attributes that have more than one value for a particular entity is called a multi-valued attribute. Different entities may have different numbers of values for these kinds of attributes. For multi-valued attributes you must also specify the minimum and maximum number of values that can be attached. For example, the phone number for a person entity is a multi-valued attribute. Stored and derived, attributes that are directly stored in the database are called stored attributes. For example, birth date, attribute of a person entity can be a stored attribute. However, there are certain attributes whose value can be computed from the value of the stored attribute. For example, in the person entity, the attribute, birth date, can be used to compute the attribute age of a person on a specific day. Thus, birth date is a stored attribute, whereas age may be a derived attribute for this entity. 3.2.3 Relationships. First, let us define the term relationships, i.e., what are relationships? A relationship can be defined as a connection or set of associations, or a rule for communication among entities. Example, in a college database, the association between student and course entity set, i.e., in the statement student opts course opts is an example of a relationship between the two entities student and course. Relationship sets. A relationship set is a set of relationships of the same type. For example, consider the relationship between two entity sets student and course. Collection of all the instances of relationship opts forms a relationship set. 3.2.4 AR Diagram Basics. The logical structure of a database is modeled using an ER model, which is graphically represented with the help of an ER diagram. The basic symbols using in an ER diagrams are given in the following table. Object represented by entity set rectangle, attribute ellipse, relationship set diamonds. Figure 3.1 shows different kinds of entities, attributes, relationships and participation constraints, which are explained in this unit. Figure 3.1, symbols of ER diagrams. Look at the screen. 3.2.5 More about relationships. In this section, you will go through some of the important concepts, which are used for making good ER models. Degree of a relationship set. The degree of a relationship set is the number of participating entity sets. The relationship between two entities is called a binary relationship. A relationship among three entities is called a ternary relationship. Similarly, a relationship among n entities is called an n-ary relationship. Cardinality of a relationship set. Cardinality specifies the number of instances of an entity associated with another entity participating in a relationship. Based on the cardinality, binary relationships can be further classified into the following categories. 1-to-1. An entity in A is associated with at most one entity in B, and an entity in B is associated with at most one entity in A. For example, the relationship headed by between college entity set and principal entity set would be 1-to-1, as one college can have at most one principal, and one principal can be principal of only one college. This example assumes that a principal can be head of only one college. Similarly, you can define the relationship between university and vice chancellor. 1-to-many, consider entity sets A and entity set B has a relationship. Cardinality A, B, as 1, n. This suggests that one specific entity of A may be related with several entities of entity set B. For example, relationship between department entity set and faculty entity set. Assuming that a faculty member can work in only one department. For example, in the diagram above, several faculty members may be appointed in one department. However, a specific faculty member will be appointed in precisely one department. Many-to-one, consider entity sets A and entity set B has a relationship. Cardinality A, B, as n, 1. This suggests that several entities of A may be related with one specific entity of entity set B. For example, the relationship between entity set course and entity set instructor. An instructor can teach various courses, but a single course can be taught only by one instructor. Please note this is an assumption. Many-to-many, entities in entity set A and entity set B are associated with any number of entities from each other. For example, consider that a course can be taught jointly by many faculty members, and each faculty member can teach several courses, then many-to-many relationship holds. Another example is shown in the diagram given below. The relationship cardinality, M, N. This implies that an author entity can be correlated to many book entities, which are written by him, her. Further, a book entity can also be correlated with several author entities who have written the book. Recursive relationships. A recursive relationship is that relationships in which both the participating entity sets are the same entity set. However, the role of the entity set in each participation is different. Participation constraints. The participation constraints specify whether the existence of an entity depends on its being related to another entity via the relationship type. There are two types of participation constraints. Total, when all the entities from an entity set participate in a relationship set, it is termed as the total participation. For example, the participation of the entity set course in the relationship set, taught by, can be said to be total because every course must be taught by a faculty. Partial, when it is not necessary for all the entities from an entity set to participate in a relationship set, it is termed as partial participation. For example, the participation of the entity set instructor in the relationship set taught by can be partial, since not every instructor may be teaching a course. 3.2.6 Extended ER features. Although the basic features of ER diagrams are sufficient to design many database situations. However, with more complex relations and advanced database Applications, it is required to use extended features of ER models. The three such features are generalization, specialization, and aggregation. We have explained them with the help of an example. More details on them are available in the further readings. Example 1. A bank has an account entity set. Any accounts of the bank can be one of two types: 1. Savings account and 2. Current account. The statement above represents a specialization, generalization hierarchy. It can be shown as Figure 3.2, Generalization and Specialization Hierarchy. Look at the screen. Aggregation. One limitation of the ER diagram is that they do not allow representation of relationships among relationships. In such a case, the relationship, along with its entities, are promoted, aggregated to form an aggregate entity which can be used for expressing the required relationships. A detailed discussion on aggregation is beyond the scope of this unit. You can refer to the further readings for more detail. 3.3 An example. Let us explain it with the help of an example application. We will describe herein example database application of a college database and use it for illustrating various ER modeling concepts. Problem statement. A college database keeps track of students, faculty, departments, and courses. Following paragraphs gives the description of a college database system. A college contains various departments like Department of English, Department of Hindi, Department of Computer Science, etc. Each department is assigned a unique hidden name. Some faculty members are appointed to each department and one of them works as head of the department. There are various courses conducted by each department. Each course is assigned a unique id, name and duration. The information contained for various objects are stated below. Faculty information contains name, address, department, basic salary, etc. A faculty member is assigned to only one department but can teach courses of another department. Students' information contains roll no, unique, name, address, etc. A student can opt only for one course and one department only. Student's parent or guardian information to be recorded as name of parent or guardian, age of the parent or guardian, gender and address of parent or guardian. A student is allowed to take only one course. A student is assisted by his/her guardian. A faculty works in a department, which is headed by a faculty member. A course is taught by a faculty, who is allowed to teach several courses. Defining entities and attributes. One of the simplest ways to identify the entities is to look for the proper nouns. This gives us possible set of entities in the problem statement are student, faculty, department, course, guardian. The attributes of these entities can be found from the statements. You may also note, except of guardian, dot, student, roll no primary key, name, address. Faculty, id primary key, name, address, basic underscore sal. Department, d underscore no, primary key, d underscore name. Course underscore id primary key, course underscore name, duration. Guardian, name, address, relationship. Please note that the guardian is a weak entity. It is related to the strong entity, student. Defining relationship. Using the concepts defined earlier, we have identified that strong entities in college database are student, faculty, course and department. This database also has one weak entity called guardian. You can specify the following relationships among these entities. Further, these relationships also show the relationship cardinality and participation constraints. 1. Head underscore of is a one relationship between faculty and department. Participation of the entity faculty is partial since not all the faculty members participate in this relationship, as all cannot be the head, while the participation from the department side is total since every department has one head. Please also note that this relationship has an attribute date underscore from, which stores the date from which the given appointment was applicable. 2. Works underscore in is a n relationship between department and faculty, as one department can have many faculty, whereas a faculty is associated with only one department. Participation from both the sides is total, as every department has at least one faculty and every faculty must belong to a department. 3. Opts is a 1N relationship between course and student. Participation from the student side is total because we are assuming that each student opts for one course, but the participation from the course side is partial, since there can be courses that have no students. 4. Taught_by is AM/N relationship between faculty and course, as a faculty can teach many courses and a course can be taught by many faculty members. 5. Enrolled is a 1N relationship between student and department as a student is allowed to enroll for only one department at a time. A student must enroll in a department. However, a newly created department may not have a student. 6. Assisted_by is a 1N relationship between student and guardian as a student can have more than one local guardian and one local guardian is assumed to be related to one student only. The weak entity guardian has total participation in the relation assisted_by. Now, you are ready to make an ER diagram for the college database. The AR diagram. Figure 3.3, ER diagram of college database. Look at the screen. 3.4 Conversion of ER diagram to relational database. A relational database management system is designed from an ER diagram, which represents various entities and relationships among entities for an application using the following methods. Conversion of entity sets. Strong entity set. For each strong entity set A in the ER diagram, you create a relation R containing all the simple attributes of E. The primary key of the relation R will be one of the key attributes of R. For example, the entities student, faculty, course and department, which are strong entities, relations as shown in figure 3.4 would be created. Student, roll no, name, address. Faculty, id, name, address, basic_sal. Department, d_no, d_name. Course, course_id, course_name, duration. Figure 3.4, Conversion of strong entities to relations. 2. For each weak entity type W in the ER diagram, you create another relation R that contains all simple attributes of W. Further, you add the key attributes of the owner entity set, say KP, of W in R. The primary key to this relation R as in foreign key is KP, which references the owner entity of W. For example, conversion of weak entity guardian into relation is shown in figure 3.5. Please note that the owner entity of the guardian entity is the strong entity student, whose key is roll number. Therefore, the key to guardian relation is roll no name. The foreign key in guardian relation is roll no, which refers to student relation. Guardian, roll no. Name, address, relationship. Foreign key, roll no refers to relation student. Figure 3.5, Conversion of weak entity guardian to relation. Conversion of relationship sets. Binary relationships. I1-to-1 relationships. For each one relationship set in the ER diagram involving two entities E1 and E2, you choose one of the two entities, say E1, preferably the one with total participation, and add the primary key attribute of the other entity E2 in the relation of entity E1. Make this added attribute in E1 relation as a foreign key attribute to the relation created from another entity, E2. You should also include all the simple attributes of the relationship type, if any, in the relation E1. For example, the head underscore of relationship in figure 3.3 is 1, 1. The two entities participating in the relationship are department and faculty. The participation of the department entity is total in the head underscore of relationship. Therefore, the ID attribute, which is the primary key of the faculty entity, is added to department relation. Please note, you can rename this attribute in the department relation if needed. In addition, this attribute in department relation will be the foreign key to the faculty relation. Further, the attribute date underscore from of the head underscore of relationship is also added to the department relation. This is shown in figure 3.6. Please note that you will keep information in this. The relation only stores the ID of the current head and date from which he is the head. Please also note that you will not create a separate table of the relationship head underscore of department D underscore no. D underscore name, head underscore ID, date underscore from. The ID attribute of faculty relations is added to department relation and has been renamed as head underscore id. Foreign key, head underscore id references ID attribute in faculty relation. Figure 3.6, converting 1 relationship, no new relation is added. 2. One-to-many or many-to-one relationships. Both relationship sets involve two entity sets, say E1 and E2. Further, assume that E1 is on the many side and E2 is on the one side of the relationship set. You just need to include the primary key of the relation of entity on the one side, E2 in the case as above, to the relation created for the entity set of many side, E1 in the present case. You should include all simple attributes, or simple components of a composite attributes of relationship set, if any, in the relation of E1. Please note that now the relation of E1 has a foreign key reference to the relation of E2. For example, the works underscore in relationship between the entities department and faculty. For this relationship, the entity at n side is faculty, therefore add primary key attribute of entity department, i.e., D underscore no as a foreign key attribute in relation created for faculty entity set. This is shown in figure 3.7. Faculty, id, name, address, basic underscore sal, D underscore no. The works underscore in relationship has been included in faculty relation. D underscore no is a foreign key and references the relation department. Figure 3.7, converting 1 n relationship to relation, no new table is added in this case. 3. Many-to-many, m, n, relationship. Consider that a n relationship set is binary with two participating entities. Say entity 1 and entity 2. For this type of relationship set a relation is created. This relationship set should contain the primary key of entity 1, sat pke1, as well as the primary key of entity 2, say pke2. In addition, any attribute of the relationship set is added to the relation. The primary key of this newly formed relation of the n relationship set is the composite primary key pke1 pke2. Please also note that for this new relation of the relationship set, there exists two foreign keys pke1, which refers to the relation of entity 1 and pke2, which refers to the relation of entity set entity 2. For example, the n relationship dot underscore by between entity sets course and faculty should be represented as a new table. The structure of the table will include the primary key of course and primary key of faculty entities. Please note that both course and faculty relations remain unchanged. Add the following relation into already existing list of relations. Dot underscore by, course underscore ID. ID, primary key, course underscore id. Foreign keys. Course underscore id references course relation. ID references faculty relation. This relation has no other attribute, as the relationship has no attribute. Figure 3.8, converting n relationship dot underscore by into relations. NRE relationships. There are several cases for creating relations for NRE relationships. A very general case is presented here. For each NRE relationship set R where n greater than 2, you create a new table S to represent R. You should include the primary key of all the participating entity sets as the foreign key attributes in S. You should include any simple attributes of the NRE relationship set, or simple components of complete attributes, as attributes of S. The primary key of S is usually a combination of all the foreign keys that reference the relations representing the participating entity sets. Figure 3.8 is a special case of NRE relationship, i.e. a binary relationship. Multivalued attributes. For each multivalued attribute, A, of an entity set A, you can create a new relation R that includes an attribute corresponding to the primary key attribute of the relation. Entity A that represents the entity set or relationship set that has as an attribute. The primary key of R is then a combination of A and the primary key of relation of E. For example, if a student entity had role no, name and phone number attributes, where phone number is a multivalued attribute, then you will create two tables for this entity as given below. Student, role no, name, phone, role no, phone number. Converting generalization, specialization hierarchy to tables. A simple rule for conversation may be to decompose all the specialized entities into relations in case they are disjoint. For example, for the ER diagram of figure 3.1, you can create the two tables as saving underscore account, account no, holder name, branch, balance, interest. Current underscore account, account no, holder name, branch, balance, charges. The other way might be to create tables that are overlapping, not disjoint. For example, assuming that in the ER diagram of figure 3.2 contains overlapping subclasses, then you would be creating the following three relations. The first relation would be for the higher level entity. Account, account no, holder name, branch, balance. The specialization entities will contain the primary key of the generalized entity and all the attributes of entity itself, as shown below. Saving, account no, interest. Current, account no, charges. Thus, the information about a single account can be found in all the three relations. 3.5 Enhanced ER Model. Enhanced ER models can help in designing of relational and object relational database systems. In addition to ER modeling concepts, the enhanced ER model includes 1. Subclass and superclass. 2. Inheritance. 3. Specialization and generalization. As discussed earlier, an entity may be an object with physical existence or it may be an object with a conceptual existence. An entity is depicted by a set of attributes. Sometimes, an entity can consist of explicit subgroupings. For example, an entity vehicle consists of subgroups truck or commercial vehicles, light motor vehicles or car, two-wheelers or scooter, etc. Every subgrouping must belong to entity set vehicle. Therefore, these subgroupings are called a subclass of the vehicle entity set and the vehicle itself is called the superclass for each of these subclasses. Figure 3.9, a class hierarchy. Look at the screen. The relationship between a superclass and any of its subclasses is called class-subclass relationship. It is often called as a relationship because of the way we refer to the concept, as you would write, car is a vehicle. The member entity of the subclass represents the same real world as the member entity of the superclass. If an entity is a member of a subclass, by default it must also become a member of the superclass, whereas it is not necessary that every entity of the superclass must be a member of its subclass. An entity that is a member of a subclass inherits all the attributes of its superclass. An entity set is identified by its attributes and the relationship sets in which it participates. Therefore, a subclass entity also inherits all the relationships in which the superclass participates. According to inheritance, the subclass inherits attributes and relationships of the superclass. In addition, every subclass can contain its own attributes and relationships in which it has participated. Specialization is a process in which an entity set, superclass, is modeled as a set of sub-entity sets, subclasses, by using a specific distinguishing characteristic of the superclass. For example, in figure 3.9, the superclass vehicle is modeled using sub-classes, truck or commercial vehicle, car or light motor vehicle, scooter or two-wheelers, using the type attribute of the vehicle class. Please note that several specializations hierarchies can be modeled using a superclass by using different distinguishing characteristics. Figure 3.10 shows how you can represent a specialization with the help of an EER diagram. Look at the screen. Figure 3.10, EER diagram showing more than one specialization from one superclass. In figure 3.10, letter D in the circle indicates that all these subclasses are disjoint in nature, i.e. all the vehicle entities are disjoint, as they can be part of only one of the subclass. Please also notice that in figure 3.10, common attributes, like vehicle number, owner name etc., are attributes of the superclass, whereas attributes like mileage of car, stock of scooter and capacity of truck are the attributes of the subclasses. Please note that an entity will be appearing twice in the EER diagram. Once in the subclass and the other in the superclass. Please refer to figure 3.11, look at the screen. Figure 3.11, sharing of members of the superclass vehicle and its subclasses. Hence, the specialization is a set of subclasses of an entity set, which establishes additional specific attributes with each subclass and establishes additional specific relationship sets between a subclass and other entity types or other subclasses. Generalization is the reverse process of specialization. In other words, it is a process of representing entity sets consisting of entities which have almost similar attributes excepting few. The similar attributes of these entity set form the super class. For example, the entity set car and truck can be generalized into entity set vehicle. Therefore, car and truck can now be subclasses of the superclass. Generalized class vehicle. Refer to figure 3.12. Look at the screen. Figure 3.12, Generalization and Specialization. Constraints and characteristics of specialization and generalization. A super class may either have a single subclass or many subclasses in specialization. In case of only one subclass, you do not use circle notation to show the relationship of subclass, superclass. Sometimes in specialization, the subclass becomes the member of the superclass after satisfying a condition on the value of some attributes of the superclass. Such subclasses are called condition-defined subclasses or predicate-defined subclasses. For example, the vehicle entity set has an attribute vehicle type, as shown in figure 3.12. You can specify the condition of membership for a subclass car, truck, scooter by the predicate vehicle type of the superclass vehicle. Therefore, a vehicle object can be a member of the subclass if it satisfies the membership condition for that subclass. For example, to be a member of subclass car, a vehicle entity must have the condition vehicle type equals car as true. A specialization in which an attribute or a set of attributes of the superclass, called the defining attribute of specialization, specify membership condition of the subclasses, is termed as attribute-defined specialization. In case no membership condition is stated for specialization, a database user determines the membership. Such specialization is termed as user-defined specialization. Disjointness is also the constraints to a specialization, which specifies that a given entity cannot be a member of more than one subclasses for a specific specialization hierarchy. For example, in figure 3.12, the symbol D in circle stands for disjointness, as an entity can be a member of a single subclass only. But if the real-world entity is not a disjoint entity, sets of the subclasses may overlap. This is represented by an O in the circle. For example, if you classify a class book into subclasses textbooks and reference books, then you may like to define a specific book in both the subclasses. This is a case of overlapping constraints. When every entity in the superclass must be a member of some subclass in the specialization, it is called total specialization. But if every entity does not necessarily need to belong to any of the subclasses, it is called partial specialization. The total is represented by a double line. This is to note that in specialization and generalization, the deletion of an entity from a superclass implies automatic deletion from subclasses belonging to the same. Similarly, insertion of an entity in a superclass results in insertion of the entity in all the subclasses for which the attributes of this entity fulfills the constraints of attribute-defined specialization. In case of total specialization, insertion of an entity in a superclass implies compulsory insertion in at least one of the subclasses of the specialization. Union, in some cases, a single class has a similar relationship with more than one class. For example, the subclass car may be owned by two different types of owners, individual or organization. Both these types of owners are different classes. Thus, such a situation can be modeled with the help of a union. 3.6 Converting EER diagram to relations. The rules for converting the EER diagram, which primarily includes specialization and generalization hierarchy, are the same as in the ER diagram. Let us recapitulate these rules. Create a relation for each strong entity set. Create a relation for a weak entity set. The primary key of this relation would be a composite key involving the attributes of the primary key of the strong entity. set on which it depends and discriminator of the weak entity. Create a relation for each binary M-N relationship set having the primary keys of both the participating entities, which form the composite primary key to the relation. The individual primary keys are the foreign keys to respective relations. For a binary M1 M relationship, in general, the primary key on the M side is added to one side of the entity. This also becomes the foreign key. For a binary 1 relationship set, the primary key of chosen participating relation is added to the other participating relation. Composite attributes may sometimes be converted to a separate relation. For generalization or specialization hierarchy, a relation can be created for higher level and each of the lower level entities. The higher level entity would have the common attributes and each lower level relation would have the primary key of the higher level entity and the attributes defined at the lower specialized level. However, for a complete disjoint hierarchy, no relation may be made at the higher level, but the relations are made at the lower level including the attributes of higher level. For an aggregation, all the entities and relationships of the aggregation are transformed into the relation on the basis of rules stated above. A relation is also created for the relationship set that exists between the aggregated entity, say age, and another simple entity, say. The primary key of this new relation is the composite key involving the primary key of the age and say. So let us now discuss the process of converting the EER diagram into a relation. In case of disjoint constraints with total participation, it is advisable to create separate relations for the subclasses. But the only problem in such a case will be to implement the referential entity constraints suitably. For example, assuming that this EER diagram can be converted into a relation as car, number, owner, mileage, scooter, number, owner, stock, truck, number, owner, capacity. Please note that referential integrity constraint in this case would require a relationship with three relations and therefore is more complex to implement. In the EER diagram of figure 3.12 there is no total participation of vehicle superclass in the subclasses, then there will be some vehicles, which are not car, scooter and truck. So how can you represent these? In addition, in case of overlapping constraints, some tuples may get represented in more than one relation. Thus, in such cases, it is ideal to create one relation for the superclass and other relations for the subclasses having the primary key and any other attributes of that subclass. For example, with no total participation, the following relations would be created for the EER diagram of figure 3.12. Vehicle, number, owner, type, car, number, mileage, scooter, number, stock, truck, number, capacity. Finally, in the case of union, since it represents dissimilar classes, you may represent separate relations. For example, both individual and organization will be modeled to separate relations. 3.7 Summary. This unit presents the concept of ER model and EER models. Both these models are represented with the help of ER diagram and EER diagram. These diagrams are very powerful tools to represent the need of data in a database system and can be used for the design of a good database system. The ER model explained in this unit covers the basic aspects of ER modeling. The unit defines the concept of entities, attributes and relationships. Further, it defines different types of entities like strong and weak entities, different types of attributes such as simple, composite, derived, etc., the cardinality and participation constraints in a relationship. These concepts are very useful and you should attempt solving related problems from the further readings. Concepts of EER diagrams including generalization, specialization, union, etc., have also been explained in this unit. You may refer to further readings for more details on ER and EER diagrams. Thank you for watching. We will see you in the next video with the next chapter.